embark on a daring journey into Earth's molten past, a primordial epoch when our planet writhed under an unimaginable geological upheaval. What primal forces transformed our nascent world into a fiery crucible 400 million years ago? A time when life hung precariously in the balance, utterly reshaped by the planet's violent convulsions. This wasn't merely a period of intense volcanism, it was a molten cataclysm that fundamentally re-engineered the very fabric of life on Earth. Prepare to witness a planet reborn in fire and ash.
Welcome, time travelers and geology enthusiasts, to an epic exploration of one of Earth's most tumultuous chapters, the Devonian period, roughly 419 to 358 million years ago. Often celebrated for the diversification of fish and the rise of Earth's first forests, this era held a darker, more dramatic secret. A secret etched in layers of rock and whispered through the fossil record. Beneath the veneer of evolving life, our planet was experiencing an unprecedented geological upheaval. An era of volcanic activity so intense it dwarfed anything humanity has ever witnessed. For those new to Earth's deep history, fear not. We will demystify complex geological terms like large igneous provinces and anoxic events, guiding you through this ancient fiery epoch with clarity and excitement. We'll delve into the raw power of plate tectonics, unravel the mysteries of Earth's atmosphere as it choked on volcanic gases, and examine how life adapted, struggled, and ultimately triumphed amidst this global inferno. This isn't just a science lesson, it's a dramatic saga of planetary transformation, a testament to the Earth's incredible power and resilience.
Imagine, if you will, our planet 400 million years ago. The supercontinent of Gondwana dominated the southern hemisphere, while smaller landmasses like Laurentia, Baltica, and Siberia began to coalesce, driven by the inexorable creep of plate tectonics. This wasn't the serene blue marble we know today. It was a world teetering on the edge of a magmatic eruption, a planet whose crust was stretched, pulled, and fractured by immense subsurface forces. The Devonian, often dubbed the Age of Fishes for its spectacular aquatic biodiversity, was simultaneously an age of fire, a period defined by a scale of volcanism that scientists are only just beginning to fully appreciate. What exactly triggered this planetary outpouring of molten rock? The answer lies deep within Earth's mantle, where colossal plumes of superheated material began their slow, relentless ascent towards the surface. These weren't your typical isolated volcanoes. We are talking about vast regions, sometimes covering hundreds of thousands of square kilometers, where magma welled up from beneath the crust, creating what geologists term large igneous provinces, or LIPs. Think of them as immense flood basalts, unimaginably larger than anything witnessed in recent geological history, precursors to the famed Siberian traps that would devastate life hundreds of millions of years later. These LIPs weren't just spectacular displays of Earth's raw power, they were harbingers of profound environmental change. The sheer volume of volcanic gases, carbon dioxide, sulfur dioxide, chlorine, fluorine, pumped into the atmosphere had cataclysmic implications for the planet's climate and, by extension, every living organism. How did this ancient Earth, still relatively young in its journey, withstand such an onslaught? And what lessons can we glean from this fiery chapter about the delicate balance that sustains life on our world? Our journey begins by setting the stage, understanding the tectonic configuration of the Devonian, and identifying the early stirrings of the geological upheaval that would define the era. Geologists piece together this ancient puzzle using evidence embedded in rock formations, paleomagnetic data that tells us where landmasses were located, and the chemical signatures locked within ancient minerals. This detective work reveals a planet in constant motion, a dynamic system where the slow dance of continents could trigger explosions of molten fury on a global scale.
When we speak of large igneous provinces in the Devonian, we are talking about events of truly staggering magnitude, dwarfing the volcanic eruptions we witness today. Imagine an eruption that doesn't just spew ash and lava from a single cone, but rather pours out through vast fissures, coating entire continents in layers of basalt. One of the most significant, though perhaps less famous than the Siberian traps or Deccan traps, is the Vilui traps in Siberia. While some of its most active phases are associated with the Permian-Triassic boundary, evidence suggests significant precursor events and magmatic pulses during the Devonian, contributing to the broader pattern of Devonian volcanism. These weren't isolated incidents. They were part of a global pattern of intense magnetism driven by mantle plumes. A mantle plume is essentially a massive upwelling of abnormally hot rock from deep within Earth's mantle, pushing against the crust above it. Think of it like a giant, superheated balloon slowly rising and pressing against a thin ceiling, eventually causing it to crack and rupture. The scale of these eruptions is almost incomprehensible. Estimates suggest that some LIPs released millions of cubic kilometers of lava over relatively short geological timescales, tens of millions of years, which, in Earth's deep time, is a blink of an eye. The sheer volume of this basaltic outpouring had profound geological impacts. It altered the very topography of continents, created vast plateaus of igneous rock, and even influenced sea levels as the massive weight of the eruptions depressed the crust. Beyond the immediate landscape changes, the process of forming these LIPs involved extensive volcanic outgassing. Each eruption wasn't just lava. It was a cocktail of gases, including enormous quantities of carbon dioxide, sulfur dioxide, methane, and various halogen compounds. These gases, once released into the atmosphere, fundamentally altered Earth's delicate climatic balance. The challenge for geologists is identifying and dating these ancient large igneous provinces. Unlike more recent volcanic events, the geological signature of Devonian LIPs has often been eroded, buried, or metamorphosed over hundreds of millions of years. Scientists rely on radiometric dating, analyzing the decay of radioactive isotopes within volcanic rocks to pinpoint the age of these eruptions. They also look for characteristic rock types, such as tholeiitic basalts, which are commonly associated with LIPs, and seek out specific geochemical signatures that can link disparate rock exposures to a single, massive magmatic event. This is where the detective work becomes truly fascinating. Imagine a team of geologists in a remote wilderness examining ancient rock outcrops, searching for clues that might reveal a lost history of planetary inferno. Every sample, every chemical analysis adds another piece to the grand puzzle of Earth's Devonian past, helping us reconstruct the scale and timing of these truly cataclysmic events.
The direct consequence of such monumental volcanic outgassing was an immediate and profound alteration of Earth's atmospheric chemistry. Imagine a sky not merely gray with ash, but thick with a cocktail of greenhouse gases and corrosive aerosols. The dominant gases released during these large igneous province eruptions included staggering quantities of carbon dioxide and sulfur dioxide, along with significant amounts of methane, hydrogen sulfide, and various halogens like chlorine and fluorine. What do these gases do to a planetary atmosphere? CO2 and CH4 are potent greenhouse gases. Their release in such massive volumes would have led to a rapid and significant warming of the planet. Think of it as Earth's own uncontrolled industrial revolution, but on a geological scale, driven by internal forces. Temperatures would have soared, leading to dramatic shifts in global climate patterns. But it wasn't just warming. The SO2 released reacted with water vapor in the atmosphere to form sulfuric acid aerosols. These fine particles, while initially causing a cooling effect by reflecting sunlight back into space, are also highly acidic. This would have led to widespread acid rain, a phenomenon far more severe than anything we experience today. Consider the impact on early terrestrial plants just beginning to colonize the land and the surface waters of the oceans. The constant barrage of acid rain would have leached nutrients from soils, damaged plant tissues, and altered the chemistry of freshwater ecosystems. Moreover, the long-term climatic impacts of a CO2-rich atmosphere would have dwarfed any short-term cooling from aerosols. The greenhouse effect would have dominated, leading to sustained periods of elevated global temperatures.
Geologists and paleoclimatologists reconstruct these ancient atmospheric conditions by studying proxies, indirect indicators preserved in the rock record. One crucial piece of evidence comes from carbon isotopes. Carbon exists in several isotopic forms, with carbon-12 being the most common and carbon-13 being less abundant. Biological processes preferentially take up 12C. When massive amounts of volcanically derived CO2, which has a distinct isotopic signature, often enriched in 12C from deep mantle sources, are released into the atmosphere and then dissolved into the oceans, it changes the isotopic ratio of carbon in seawater. This change is then recorded in the shells of marine organisms and in carbonate rocks, leaving a telltale fingerprint of major carbon cycle perturbations. By analyzing these isotopic shifts, scientists can infer periods of intense volcanic outgassing and understand its profound impact on Earth's ancient climate. Could our modern industrial emissions offer a glimpse, however faint, of the atmospheric chaos that gripped the Devonian? It's a sobering thought, isn't it?
The colossal influx of greenhouse gases from the molten cataclysm of Devonian volcanism didn't just warm the atmosphere. It initiated a cascade of environmental crises that rippled through Earth's oceans. A warmer atmosphere directly leads to warmer oceans. As ocean temperatures rise, the solubility of gases, particularly oxygen, in seawater decreases. Think of a can of soda. It goes flat faster when warm because the dissolved CO2 escapes more readily. The same principle applies to oxygen in the ocean. Less dissolved oxygen means marine environments become increasingly oxygen depleted. This process is known as ocean anoxia, where large areas of the ocean become devoid of oxygen, turning them into biological dead zones. The consequences of widespread anoxia are devastating for marine life. Most complex marine organisms, from the diverse fish that define the Devonian to the intricate coral reefs, require oxygen to survive. As oxygen levels plummeted, vast stretches of the seafloor would have become uninhabitable. Only specialized anaerobic bacteria could thrive in these poisoned waters, often producing hydrogen sulfide, H2S, a highly toxic gas that would have further exacerbated the problem, creating what scientists refer to as euxinic conditions. Imagine the vibrant, fish-filled seas of the early Devonian gradually transforming into murky, stinking cesspools filled with the ghostly remains of creatures unable to adapt to the suffocating conditions. This wasn't a localized problem. Evidence suggests multiple, widespread anoxic events occurred throughout the Devonian, particularly towards the latter half of the period, coinciding with peaks in volcanic activity. The evidence for these anoxic events comes from the geological record itself. Scientists look for specific types of sedimentary rocks, particularly black shales, which form in oxygen-depleted environments where organic matter can be preserved without being decomposed by oxygen-breathing organisms. The presence of pyrite, iron sulfide, and specific biomarkers, molecular fossils from anaerobic bacteria, further confirms the anoxic conditions. Furthermore, carbon isotope anomalies found in these sedimentary layers provide a direct link to the massive carbon injections from volcanism, reinforcing the connection between eruptive events, global warming, and ocean deoxygenation.
How precisely did these anoxic events impact the rich marine biodiversity of the Devonian? It's a complex question, but the correlation between these geological signatures and periods of significant biodiversity loss is compelling. The Devonian oceans, once teeming with life, faced a suffocating challenge orchestrated by the very planet beneath them. This intricate interplay between geological forces and biological responses highlights the profound fragility of Earth's life support systems.
The Devonian period is not only renowned for its biological innovations, but also for experiencing one of Earth's Big Five mass extinction events. The Late Devonian Extinction, also known as the Frasnian-Famanin Extinction Event. This catastrophic period of biodiversity loss, occurring in several pulses towards the end of the Devonian, saw the demise of a substantial portion of marine species, including many reef-building organisms, brachiopods, and various fish groups. For decades, the exact cause of this extinction has been a subject of intense scientific debate. Was it an asteroid impact, climate change, or something else entirely? A growing body of evidence, however, points to the profound and often overlooked role of the Devonian's immense volcanic activity as a primary driver. The timing is often striking. Peaks in volcanic activity, particularly the emplacement of large igneous provinces like parts of the Vili Traps and other less defined magmatic events, appear to correlate with specific extinction pulses. The argument is not that the lava flows themselves killed off species directly, though localized destruction would have been immense, but rather that the cascading environmental effects triggered by sustained outgassing were the true culprits. The primary mechanism is thought to be the sequence we just discussed: massive CO2 emissions leading to global warming, followed by widespread ocean anoxia and acidification. The oceans, already stressed by warming, became increasingly hostile environments for oxygen-breathing life. The evidence for this linkage comes from a multi-proxy approach. Geologists observe the temporal coincidence of magmatic events with extinction horizons. Paleontologists document the sharp declines in biodiversity in the fossil record. And geochemists provide the crucial missing link through isotopic analyses. For instance, negative carbon isotope excursions, shifts towards lighter carbon isotopes, are observed in sedimentary rocks around the Frasnian-Famanin boundary. These excursions are interpreted as a signature of massive injections of volcanically derived CO2 into the atmosphere and oceans, which subsequently led to a significant perturbation of the global carbon cycle. Such shifts strongly suggest a link between major volcanic events and the environmental changes that preceded the extinctions.
While some scientists still debate the precise contribution of volcanism versus other potential factors, like asteroid impacts, though evidence for a major Devonian impact causing widespread extinction remains elusive, the weight of geological and geochemical evidence increasingly supports a dominant role for the ancient fiery epoch in orchestrating the late Devonian extinction. This isn't to say it was the only factor, but rather a profound trigger that pushed Earth's biosphere past a critical threshold. The Devonian extinctions serve as a stark reminder that even seemingly slow geological processes can unleash cataclysmic consequences for life, illustrating the intricate and often volatile relationship between our living planet and its deep geological heart. Beyond the atmospheric and oceanic impacts, the sheer scale of the Devonian's molten cataclysm irrevocably altered Earth's physical geography. Imagine not just isolated volcanoes, but vast, continent-sized wounds from which molten rock flowed, creating immense plateaus of basalt. These events, driven by large igneous province formation, were not just localized eruptions, they were regional transformations. Basalt floods, as they are called, involve the eruption of highly fluid basaltic lava from extensive fissure vents rather than a central cone. This lava can flow for hundreds of kilometers, blanketing vast areas with successive layers, building up immense stacks of dark, dense rock. The cumulative effect of these floods over millions of years was the creation of enormous, elevated igneous provinces, reshaping entire continental blocks. One of the most profound geological impacts was the direct effect on tectonic activity. The ascent of mantle plumes and the eruption of LIPs are intrinsically linked to the forces of plate tectonics. Plumes can push up the overlying lithosphere, leading to continental rifting and the breakup of supercontinents. While the major breakup of Pangaea occurred much later, the Devonian was a period of ongoing continental collision and subduction interspersed with periods of rifting and the opening of new ocean basins. The immense volumes of magma generated by plumes could have weakened the crust, making it more susceptible to tensional forces, further promoting rifting and spreading. This interplay between deep Earth processes and surface tectonics creates a dynamic feedback loop.
The weight of these enormous basaltic accumulations also caused isostatic depression of the crust. Think of it like a heavy weight placed on a raft floating on water. The raft sinks lower. Similarly, the immense mass of newly emplaced basalt caused the underlying crust to subside, forming large sedimentary basins adjacent to the igneous provinces. These basins often became traps for organic matter, contributing to the formation of future fossil fuels. Over hundreds of millions of years, these ancient basalt floods have been subjected to erosion, uplift, and further tectonic activity. Yet their remnants are still found today, offering tantalizing glimpses into this fiery past. Geologists meticulously map these ancient lava fields, analyzing their thickness, composition, and extent to reconstruct the immense scale of these geological upheavals. Each layer tells a story of a planet actively reshaping itself, a monumental testament to the relentless power of its internal engine. Amidst this molten cataclysm, a remarkable story of adaptation and resilience unfolded in Earth's biosphere. The Devonian period, despite its fiery trials, is famously known as the Age of Fishes and the time when early forests began to colonize the land. How did life not just survive, but actually thrive and diversify in a world racked by such intense geological forces? This is where the narrative shifts from raw planetary power to the tenacity of life itself, showcasing its incredible capacity to evolve and adapt to extreme conditions. In the oceans, the fish diversification was nothing short of extraordinary. Armored placoderms, predatory cartilaginous fish, and the first bony fish, including the ancestors of modern ray-finned and lobe-finned fish, swam the Devonian seas. This diversification was driven by a complex interplay of factors, including the evolution of jaws, paired fins, and specialized sensory organs. While the anoxic events of the late Devonian undoubtedly culled many marine lineages, earlier parts of the period saw a flourishing of aquatic life. It's plausible that periods of high productivity, fueled by volcanic nutrient input in certain areas, might have contributed to localized bursts of evolution, even as other regions faced environmental stress. However, the ultimate impact of the extinction events emphasizes the fragility of even diverse ecosystems when faced with overwhelming planetary change.
On land, a revolution was underway. The Devonian witnessed the ascent of Earth's first true forests, dominated by plants like Archaeopteris, a tree with a fern-like foliage and a robust, woody trunk. This was a monumental evolutionary step. Before this, terrestrial life was largely limited to low-lying mosses and small vascular plants. The development of deep root systems allowed plants to anchor themselves and access nutrients from deeper soil layers, fundamentally altering terrestrial landscapes.
The growth of these forests had profound impacts on the planet. They began to draw down atmospheric carbon dioxide through photosynthesis, potentially counteracting some of the volcanic greenhouse effect over geological timescales. They also stabilized soils, increased weathering rates, and created new habitats for the burgeoning terrestrial fauna. The interplay between the intense geological upheaval and the rapid evolution of life is a fascinating paradox. While volcanism presented existential threats, it also provided raw materials and dynamic environments that could spur evolutionary innovation. The very stresses imposed by a volcanic Earth might have acted as selective pressures, favoring organisms with adaptive traits that allowed them to cope with fluctuating temperatures, oxygen levels, and nutrient availability. The rise of forests and the explosion of fish diversity weren't simply coincidences. They were intertwined chapters in the dramatic saga of life finding its way on a planet in constant flux. The Devonian reminds us that life's story is often written not just in serene periods of stability, but also in the crucible of planetary crisis.
How do we know any of this? How can scientists peer back 400 million years to understand the molten cataclysm that reshaped Earth? The answer lies in the meticulous, painstaking work of deciphering the fossil record and the geological archives. Every layer of rock, every ancient fossilized organism, every chemical signature preserved in the sediments tells a part of the story. Paleontologists, like detectives of deep time, unearth and interpret the remains of ancient life. The sudden disappearance of certain species or the appearance of others in specific rock layers provides direct evidence of evolutionary events and extinctions. For instance, the dramatic drop in diversity of certain marine invertebrate groups and early fish at the Frasnian-Flaminian boundary is clearly visible in the fossil record globally, signaling a major biological crisis. But fossils don't just tell us who lived and died, they can also reveal environmental conditions. The morphology of ancient corals can tell us about ocean temperatures and water clarity. The presence or absence of certain types of microfossils, like conodonts, can indicate specific oceanic conditions, including oxygen levels. Beyond the organisms themselves, the sedimentary rocks enclosing the fossils offer crucial clues. As mentioned earlier, the presence of black shales, rich in organic carbon and often associated with pyrite, strongly indicates periods of ocean anoxia. These dark layers are like grim epitaphs for ecosystems suffocated by a lack of oxygen. Crucially, geochemical evidence complements the fossil record, providing direct insights into past atmospheric and oceanic chemistry. The study of carbon isotopes is particularly powerful. We briefly touched upon it earlier, but let's delve a bit deeper. Carbon exists in two stable isotopes, 12C and 13C. During photosynthesis, organisms preferentially take up the lighter 12C. When large amounts of organic matter are buried, for example in anoxic conditions where decomposition is limited, the remaining carbon in the ocean and atmosphere becomes relatively enriched in 13C. Conversely, a massive release of CO2 from volcanoes or the oxidation of ancient organic matter can lead to a relative decrease in 13C in the global carbon reservoir. The distinct negative carbon isotope excursions observed in Devonian sediments strongly point to massive volcanic outgassing, correlating precisely with periods of environmental stress and extinction.
This interdisciplinary approach, combining paleontology, stratigraphy, the study of rock layers, and geochemistry, allows scientists to build a coherent picture of the Devonian world. It's a continuous process of discovery and refinement. Imagine a paleontologist in a remote quarry in the Catskills, carefully chipping away at shale, hoping to find a fish fossil. At the same time, a geochemist in a lab hundreds of miles away is analyzing a tiny rock sample for its isotopic signature. Both are contributing pieces to the grand narrative of Earth's ancient fiery epoch, providing tangible evidence that allows us to explore a world so dramatically different from our own. To truly comprehend the molten cataclysm of the Devonian, we must descend into the Earth's engine room, the dynamic realm of plate tectonics. The continents we recognize today are merely the fragmented pieces of a grand, ever-changing jigsaw puzzle, constantly moving and interacting atop the viscous mantle. During the Devonian, the configuration of these plates was fundamentally different from today. The vast supercontinent of Gondwana sprawled across the southern hemisphere, while Laurentia, Proto-North America, Baltica, Proto-Europe, and Siberia were distinct landmasses. These continental blocks were not static. They were engaged in a slow, relentless dance of collision, rifting, and subduction that provided the ultimate geological stage for the intense volcanism of the era.
One of the primary drivers of Devonian volcanism was the process of subduction, where oceanic crust plunges beneath another oceanic plate or a continental plate. It melts as it descends into the hot mantle. This molten material then rises to the surface, forming volcanic arcs. The Devonian was a period of active subduction zones, particularly around the margins of Laurentia and Baltica, as they moved towards collision to form the supercontinent Euramerica, also known as Laurussia. This process would have created extensive volcanic chains, similar to the modern Ring of Fire around the Pacific Ocean. However, these archvolcanoes, while significant, likely don't fully account for the scale of the large igneous provinces, LIPs, that characterize the Devonian's intense magmatism.
For the truly massive basalt floods and LIPs, the primary driver is thought to be mantle plumes. These are columns of unusually hot rock that rise from the deep mantle, sometimes even from the core mantle boundary. When a mantle plume reaches the base of the lithosphere, Earth's rigid outer layer, it causes the crust to dome upwards and, crucially, to melt extensively. This widespread melting generates colossal volumes of magma that erupt through vast fissures rather than discrete volcanic cones. The location of these plumes is often independent of plate boundaries, meaning they can cause volcanism in the middle of continental plates. The Devonian may have seen several such plumes impacting the base of continental crusts, creating the broad regional geological upheaval that defines the period's igneous activity. Furthermore, the ongoing continental collisions that characterize the Devonian, such as the Caledonian orogeny, also played a role. While seemingly counterintuitive, collision zones can sometimes lead to localized volcanic activity through processes like crustal thickening and subsequent decompression melting, or by trapping and melting subducted oceanic slabs. The interplay of these forces, subduction-related archvolcanism, mantle plume-driven LIPs, and even localized magmatism from continental collisions, created a geological cocktail that fueled the ancient fiery epoch. Understanding these tectonic forces is key to unlocking the true narrative of Earth's transformation, revealing how the planet's internal dynamics directly dictated its surface environment and the fate of its evolving biosphere.
We've touched upon anoxic events as a consequence of Devonian volcanism and global warming, but let's delve deeper into their profound and often overlooked impact on marine life. Anoxic conditions, the absence of oxygen, represent an environmental tipping point for most complex life forms. The Devonian oceans, once teeming with diverse fish, corals, and invertebrates, periodically transformed into hostile, suffocating environments. This wasn't a uniform process across all ocean basins. Certain areas, particularly restricted basins or deep water environments, would have been more susceptible to becoming anoxic. However, evidence suggests multiple widespread anoxic events during the Devonian, indicating a global perturbation of ocean chemistry. The process often begins with the increased stratification of the water column. As surface waters warm due to the greenhouse effect, they become less dense, and thus less likely to mix with cooler, deeper, oxygen-rich waters.
This lack of circulation prevents oxygen from replenishing the deeper layers. Simultaneously, increased nutrient input, perhaps from enhanced weathering of volcanically exposed rocks, or increased continental runoff due to warmer, wetter climates, can lead to massive algal blooms in surface waters. When these algae die, they sink to the bottom and their decomposition consumes vast amounts of oxygen. In a stratified ocean, this oxygen is not replaced, leading to a vicious cycle of deoxygenation. When oxygen levels drop to near zero, the ocean chemistry shifts dramatically. Anaerobic bacteria, those that thrive without oxygen, take over the decomposition process. Many of these bacteria produce hydrogen sulfide, H2S, as a byproduct of their metabolism, turning the deep ocean into a toxic, putrid environment. This is what geologists refer to as euxinic conditions, anoxic and sulfidic. Picture a marine environment where only a few specialized extremophiles can survive, a world utterly alien to our modern, oxygen-rich oceans. The impacts on Devonian marine ecosystems were catastrophic. Organisms unable to escape these toxic waters would have perished, their remains often preserved in the oxygen-depleted sediments, forming the characteristic black shales that serve as a testament to these environmental crises.
The recurrence of these anoxic events throughout the Devonian, particularly at specific intervals coinciding with biotic crises, underscores their role as a major stressor. While the ultimate triggers were the sustained volcanism and global warming, the anoxic conditions were the immediate killing mechanism for many marine species. Understanding these ancient anoxic events is not just an academic exercise. It offers crucial insights into the vulnerability of our modern oceans to deoxygenation, a growing concern in the face of ongoing climate change. The Devonian provides a chilling historical parallel, a stark reminder of what happens when the delicate balance of planetary life support systems is pushed beyond its limits by geological upheaval. The Devonian period, prior to its dramatic end, was a golden age for marine biodiversity, particularly for the development of complex ecosystems like coral reefs. These weren't the coral reefs we know today, built predominantly by scleractinian corals. Instead, Devonian reefs were primarily constructed by tabulate and rugose corals, along with stromatoporoids, sponge-like organisms. These ancient reef systems were massive, forming extensive structures that provided habitat and food for a spectacular array of marine life, from trilobites and brachiopods to the increasingly diverse fish fauna. They were the vibrant, bustling metropolises of the Devonian seas, showcasing the pinnacle of marine ecological complexity for their time. However, these magnificent reef ecosystems were particularly vulnerable to the environmental changes brought about by the Devonian's molten cataclysm. Reef-building organisms are highly sensitive to changes in ocean temperature, water clarity, and crucially, ocean chemistry, particularly pH and oxygen levels. As volcanic outgassing led to global warming and subsequent ocean acidification, as excess CO2 dissolved in seawater, the ability of these organisms to build their calcium carbonate skeletons would have been severely compromised. Imagine trying to build a house when your very building materials are dissolving around you. This is the challenge Devonian reef builders faced.
Furthermore, the widespread anoxic events would have dealt a devastating blow to these ecosystems. Reefs require well-oxygenated, shallow waters to thrive. As deeper waters became anoxic and the anoxic zones expanded upwards, they would have encroached upon the reefs, suffocating the delicate polyps and other reef inhabitants. The combination of warming, acidification, and deoxygenation created a triple whammy that proved catastrophic for these ancient reef systems. The fossil record clearly shows a significant decline, and in many cases, outright collapse of Devonian reef ecosystems during the late Devonian extinction events. This was not a gradual decline, but a rapid, profound loss of complex ecological structures.
The demise of the Devonian reefs is a somber reminder of the sensitivity of these biodiversity hotspots to global environmental change. Their vulnerability offers a powerful parallel to the challenges faced by modern coral reefs today, which are similarly threatened by ocean warming, acidification, and deoxygenation. By studying the patterns of reef collapse in the Devonian, scientists gain crucial insights into the tipping points for these critical ecosystems. Insights that are invaluable for understanding and mitigating the impacts of current environmental crises. The ancient fiery epoch didn't just transform land masses, it profoundly reshaped the very architecture of life in the oceans, leaving behind a legacy of both magnificent diversity and profound loss.
While the marine realm bore the brunt of the molten cataclysm's immediate impact, the burgeoning terrestrial ecosystems of the Devonian also faced significant challenges and underwent remarkable transformations. The Devonian was the period when life truly began to conquer the land. We've talked about the rise of the first forests, but this also paved the way for the diversification of early terrestrial invertebrates, and crucially, the very first vertebrates to venture onto land, the tetrapods. How did these nascent land ecosystems cope with a planet in such geological turmoil? The primary challenge for terrestrial life would have been the altered atmospheric chemistry and climate. Acid rain, a direct consequence of massive sulfur dioxide emissions, would have damaged early plant life, leaching nutrients from the soil and potentially inhibiting growth. Fluctuating temperatures and altered precipitation patterns due to global warming would have created periods of stress, potentially leading to droughts or excessive humidity. However, unlike marine life, which could be directly suffocated by anoxic waters, terrestrial organisms might have had more localized refugia. Elevated CO2 levels, while driving warming, could also have acted as a fertilizer for early plants, promoting growth in some instances, though the overall balance of environmental stressors would have been negative. Despite these challenges, the evolutionary march on land continued. The development of deeper root systems in plants like Archaeopteris not only stabilized soils, but also made them more resilient to environmental fluctuations. These early forests created complex microhabitats, offering shelter and resources for early arthropods and the emerging tetrapods. The transition of fish-like ancestors to early tetrapods, those four-limbed vertebrates, occurred during the late Devonian. This was a monumental evolutionary step, allowing vertebrates to exploit a whole new range of ecological niches. Organisms like Ichthyostega and Acanthostega, with their robust limbs and lungs, were adapted to navigating shallow, oxygen-poor waters and potentially venturing onto land.
This emergence of tetrapods during a period of intense geological upheaval is a testament to life's adaptability. It suggests that environmental pressures, however severe, can sometimes drive evolutionary innovation, pushing organisms to develop novel traits that allow them to survive and thrive in new environments. Perhaps the very anoxia and warming in the aquatic realm provided a strong selective pressure for some fish lineages to develop adaptations for air breathing and terrestrial locomotion, leading to the pivotal step in vertebrate evolution. The Devonian terrestrial world, though still rudimentary compared to today's lush biomes, was a dynamic stage where life was constantly experimenting, adapting, and finding new ways to flourish, even as the planet itself raged with molten fury. Accurately dating ancient volcanic events, especially those from 400 million years ago, presents a formidable scientific challenge. Unlike historical eruptions, we don't have written records or eyewitness accounts. Yet, pinpointing the timing of large igneous provinces, or LIPs, and correlating them with climate shifts and extinction events is crucial for understanding the Devonian's molten cataclysm. How did geologists achieve this remarkable feat, peering back into deep time with such precision? The primary tool is radiometric dating. Radiometric dating relies on the predictable decay of radioactive isotopes within minerals. When molten rock cools and crystallizes, certain radioactive isotopes like uranium-lead, UPB, or argon are incorporated into the newly formed minerals. These parent isotopes then decay into stable daughter isotopes at a known constant rate. By measuring the ratio of parent to daughter isotopes in a mineral sample, scientists can calculate the age of the rock. For example, in the UPB system, uranium-238, 238U, decays to lead-206, 206 Pb with a half-life of 4.47 billion years, while uranium-235, 235U, decays to lead-207, 207 Pb with a half-life of 704 million years. By using multiple isotope systems, scientists can cross-check their results and achieve greater accuracy. However, applying these techniques to ancient volcanic rocks isn't always straightforward. Over millions of years, rocks can undergo metamorphism, where heat and pressure alter their mineralogy and potentially reset their isotopic clocks. Weathering can also leach isotopes, distorting the original age signal. Contamination from older or younger rocks can introduce errors. Imagine trying to read a clock that has been submerged, scratched, and subjected to extreme temperatures for centuries. Scientists must carefully select pristine samples, often from deeply buried core samples or well-preserved outcrops, and employ sophisticated laboratory techniques to isolate and analyze the target minerals.
Despite these challenges, significant triumphs have been made in dating Devonian volcanism. Advances in analytical precision, such as high-precision UPB zircon geochronology, have allowed scientists to date volcanic ash layers and igneous intrusions with remarkable accuracy, often to within a few 100,000 years. These precise dates are then correlated with the geological timescale and the timing of biological events, allowing scientists to establish cause and effect relationships. For example, if a precise date for a major LIP eruption closely matches the timing of a significant carbon isotope anomaly and an extinction pulse, it strengthens the argument for a volcanic trigger. The quest to precisely date these ancient events is a continuous scientific endeavor, each new date bringing us closer to understanding the true tempo and scale of Earth's ancient fiery epoch.
Our journey through the Devonian's molten cataclysm offers more than just a scientific narrative. It prompts profound philosophical reflections on humanity's place in Earth's grand, volatile history. We, as a species, have a relatively short existence on this planet, yet we are irrevocably linked to billions of years of geological and biological evolution. The forces that shaped the Devonian world, the immense power of plate tectonics, the relentless outpouring of magma, the dramatic shifts in climate, are the very forces that continue to shape our planet today, albeit often on timescales far beyond human comprehension. Consider the sheer scale of the geological upheaval we've explored. Imagine a world where temperatures soar, where oceans turn anoxic, and where landscapes are fundamentally reshaped by basalt floods. This wasn't some distant, abstract event. It was a fundamental chapter in the story of the planet that gave rise to us. Our very existence is built upon the foundation of these past planetary transformations. The carbon locked away in ancient sedimentary rocks, some of it a direct legacy of Devonian life and subsequent anoxic events, now fuels our industrial society. The very land beneath our feet bears the scars and triumphs of countless geological cycles, including periods of molten fury. This historical perspective underscores our relative fragility and the immense power of natural systems. While humanity now possesses the capacity to significantly alter Earth's climate through greenhouse gas emissions, the Devonian reminds us that the planet has experienced far greater geological events that have reshaped life on a global scale. Yet, this is not an excuse for inaction. Rather, it's a call for humility and understanding. By studying Earth's deep past, we gain crucial insights into the planet's tipping points, its resilience, and its vulnerabilities. We learn that while life is incredibly tenacious, it is not invincible. What does it mean to be a species that is both a product of deep time and an agent of rapid, unprecedented change? The ancient, fiery epoch of the Devonian serves as a powerful mirror, reflecting the profound interconnectedness of geological processes, climate, and life. It challenges us to think beyond our immediate horizons, to consider our impact on the planet in the context of its vast, dynamic history. Our scientific quest to understand the Devonian is, in a way, a quest for self-understanding, a recognition that our destiny is inextricably linked to the ongoing geological narrative of this remarkable, ever-changing planet. This journey through Earth's fiery past is not just about rocks and fossils, it's about our shared story on a planet of immense power and profound beauty.
To truly appreciate the magnitude of the Devonian's molten cataclysm, it's helpful to compare it with other periods of intense volcanism in Earth's history, particularly those associated with major extinction events. While the Devonian large igneous provinces, LIPs, might not be as widely recognized as, say, the Siberian traps or the Deccan traps, their impact was no less profound. What makes the Devonian unique, and how does its volcanic narrative compare to these other geological behemoths? The Siberian traps, erupting at the Permian-Triassic boundary around 252 million years ago, are widely considered the cause of Earth's most severe mass extinction, the Great Dying, which annihilated over 90% of marine species and 70% of terrestrial vertebrate species. The scale of the Siberian trap's basaltic outpouring was truly immense, estimated to be several million cubic kilometers of lava released in a relatively short period of about 1 to 2 million years. The resulting release of greenhouse gases, sulfur dioxide, and halogens led to extreme global warming, ocean anoxia, ocean acidification, and ozone depletion. The Deccan traps in India, responsible for the Cretaceous-Paleogene extinction event at 66 million years ago that wiped out the non-avian dinosaurs, also represent a colossal LIP, though perhaps slightly smaller in volume than the Siberian traps. While the exact volume and timing of Devonian LIPs are still being refined, the available evidence suggests magmatic events of comparable, though perhaps slightly less concentrated scale to these later supereruptions. What sets the Devonian apart is the context of life's evolution. During the Permian-Triassic transition, complex terrestrial ecosystems were well established. In the Devonian, land plants were just beginning to form forests, and terrestrial animals were still relatively primitive. The geological upheaval of the Devonian thus occurred at a critical juncture in the evolution of complex life, impacting nascent ecosystems rather than fully mature ones. This could have meant different vulnerabilities and different evolutionary pressures.
Another key difference lies in the nature of the magmatism itself. While both the Siberian and Deccan traps are strongly linked to mantle plumes, the Devonian may have seen a more dispersed, though cumulatively massive, pattern of volcanism, potentially involving multiple smaller, yet still significant LIPs, alongside extensive arc volcanism. The impact mechanisms, however, remain eerily similar. Massive outgassing leading to global warming, ocean deoxygenation, and acidification. The comparative analysis reinforces a chilling pattern. Whenever Earth experiences sustained, large-scale molten cataclysms, the biosphere inevitably faces existential threats. The Devonian serves as a crucial earlier chapter in this recurring geological drama, demonstrating the long-term, profound consequences of Earth's internal dynamism on the surface world.
Understanding the climatic effects of the Devonian's molten cataclysm requires meticulous paleoclimate reconstruction, a scientific detective story that pieces together ancient temperature records, atmospheric compositions, and oceanic conditions. How do scientists read Earth's ancient thermostat, and what insights do these reconstructions provide about the severity of the Devonian greenhouse? One of the primary tools for reconstructing past temperatures is the analysis of oxygen isotopes, 18O over 16O, in ancient minerals and fossils. The ratio of heavy oxygen, 18O, to light oxygen, 16O, in marine carbonates like shells or limestones is temperature dependent. In warmer waters, organisms tend to incorporate more of the lighter isotope. By carefully analyzing these ratios in well-preserved Devonian marine fossils, like conodonts or brachiopods, scientists can estimate the ambient water temperatures at the time these organisms lived. Similarly, the isotopic composition of carbon in organic matter can provide clues about the global carbon cycle and CO2 level. Another crucial proxy for atmospheric CO2 is the stomatal index of ancient plants. Stomata are tiny pores on the surface of plant leaves that regulate gas exchange. Plants tend to have fewer stomata when atmospheric CO2 levels are high, as they don't need as many pores to capture enough carbon for photosynthesis. By examining fossilized plant cuticles from the Devonian, paleobotanists can estimate past CO2 concentrations, offering a direct window into the atmosphere of the ancient world. These plant records, while offering valuable insights, can be localized and require careful interpretation.
Combining these proxy records with geological evidence of large igneous provinces and black shale deposition, indicative of anoxia, allows scientists to build comprehensive climate models of the Devonian. These models, essentially sophisticated computer simulations, can then test various scenarios of volcanic outgassing to see which best matches the geological and paleontological evidence. The emerging picture for the Devonian is one of significant, though perhaps fluctuating, global warming, punctuated by rapid increases in CO2 during periods of intense volcanism. Some models suggest that atmospheric CO2 levels during peak Devonian volcanism could have reached several thousand parts per million, far exceeding present-day levels of around 420 ppm. These reconstructions paint a vivid picture of a planet grappling with a powerful greenhouse effect driven by its own internal forces. They highlight the sensitivity of Earth's climate system to massive carbon injections, a crucial lesson for our own era. The challenge and the triumph of paleoclimate reconstruction lies in its ability to bring to life the invisible forces that governed Earth's ancient past, showing us how a molten cataclysm fundamentally reset Earth's thermostat with profound implications for life.
Our understanding of the Devonian's molten cataclysm and its impact on life is fundamentally rooted in the paleontological evidence meticulously unearthed and analyzed by dedicated scientists. Imagine the thrill of a paleontologist carefully exposing a fossilized fish from a 400-million-year-old rock, knowing that this single specimen holds clues to a lost world. The Devonian period, as we've noted, is often called the Age of Fishes, and for good reason. The fossil record of fish from this period is incredibly rich and diverse, offering unparalleled insights into their evolution and the ecosystems they inhabited. From the heavily armored placoderms, like the fearsome Dunkleosteus, a giant apex predator with massive bony plates, to the emergence of the first cartilaginous fish, sharks and rays, and bony fish, the Devonian seas teemed with aquatic innovation. The discovery of remarkably preserved specimens, often in sites like the Gogo Formation in Western Australia, allows paleontologists to study the intricate anatomy of these ancient creatures, providing clues about their diet, locomotion, and ecological roles. The presence and distribution of these diverse fish faunas
can also tell us about paleogeography and the connectivity of ancient oceans, which were influenced by the shifting continents. Beyond fish, the Devonian fossil record reveals a vibrant, if alien, marine world. Trilobites, those iconic arthropods, continued to diversify, although many lineages would ultimately succumb to the late Devonian extinction. Brachiopods, crinoids, and a variety of other invertebrates formed complex benthic communities. And, as we discussed, the unique Devonian coral reefs, built by tabulate and rugose corals and stromatoporoids, are extensively preserved in certain rock formations, offering a window into the structure of these ancient marine metropolises. The sudden disappearance or significant decline of these reef builders at specific stratigraphic levels provides direct paleontological evidence of environmental crises, often correlating with geochemical anomalies indicative of volcanism.
Another speculative angle involves the long-term evolutionary consequences. Could the repeated environmental stresses, the geological upheavals, and subsequent ecological collapses have acted as a powerful selective pressure, driving rapid evolutionary change? The idea is that only the most resilient and adaptable organisms would survive these bottlenecks, leading to survivor lineages that were pre-adapted to future environmental shifts. This concept of punctuated equilibrium, where long periods of stasis are interrupted by rapid evolutionary bursts driven by environmental change, aligns well with the dramatic shifts seen in the Devonian fossil record. While we can never truly experience this ancient fiery epoch, these speculative exercises allow us to vividly imagine the struggles and triumphs of life against a backdrop of unimaginable planetary forces. They transform the dry facts of geology into a dramatic saga, making the 400-million-year-old molten cataclysm feel profoundly relevant to our understanding of life's resilience and the planet's untamed power.
On land, the fossil evidence of early terrestrial ecosystems is equally compelling. The remains of early vascular plants, from small, simple forms like Cooksonia to the awe-inspiring Archaeopteris forests, are found globally. These fossils, sometimes preserved in exquisite detail, allow paleobotanists to study the morphology, reproductive strategies, and ecological roles of Earth's first land flora. The footprints and trackways of early tetrapods, like those discovered in Poland, offer tangible proof of vertebrates making their first tentative steps onto land. The sheer volume and diversity of the Devonian fossil record provide the biological context for understanding the devastating impacts of the ancient fiery epoch. Each fossil is a silent witness to a world reshaped by molten fury, offering invaluable clues that help us reconstruct the triumphs and tragedies of life in deep time.
As we delve into the cataclysmic implications of the Devonian's molten cataclysm, it's natural to engage in speculative scenarios. What would it have been like to live through such a period? How would life survive or even thrive on a volcanic Earth? While purely hypothetical, these thought experiments, grounded in scientific understanding, can help us grasp the true scale of the challenges and the remarkable tenacity of life. Imagine being an early tetrapod, newly venturing onto land, only to find the air thick with volcanic gases, the ground periodically shaking, and acid rain lashing down. Survival would demand extreme adaptability. Organisms living near volcanic vents might have faced direct heat and toxic fumes, but perhaps also found new niches. Extremophiles, organisms that thrive in extreme conditions, might have been the true champions of a volcanic Earth. We know from modern observations that some bacteria and archaea flourish around hydrothermal vents in the deep sea, feeding on sulfur and other chemicals. Could similar, perhaps even more diverse extremophile communities have flourished in Devonian volcanic environments, deriving energy from the planet's internal heat and chemistry? This possibility opens up fascinating avenues for astrobiological parallels, which we'll discuss later. For more complex life, the key to survival would have been refugia, isolated areas less affected by the immediate cataclysm. Perhaps certain highland regions or deeper ocean basins, temporarily shielded from the worst of the anoxia and acidity, would have provided safe havens for populations to weather the storm. The ability to migrate, if possible, would have been crucial, allowing species to escape directly affected zones. For marine organisms, the development of greater mobility, seen in the diversification of fish, would have been a significant advantage, enabling them to seek out more hospitable waters.
As we journey through the Devonian's molten cataclysm, it's easy to think of these events as abstract, distant occurrences. Yet the enduring legacy of this ancient fiery epic is literally etched into the very landscapes we inhabit today. Many of the rocks that form our mountains, valleys, and even the bedrock beneath our cities bear the indelible marks of the Devonian period, silently narrating a story of intense geological activity and profound environmental change. Consider the vast stretches of North America, particularly the Appalachian Mountains and the Catskill Delta region. During the Devonian, this area was part of the continent Laurentia, which was actively colliding with Baltica and Avalonia, driving intense mountain building, the Acadian orogeny. The erosion of these rising mountains shed vast quantities of sediment into the surrounding seas, forming thick sequences of Devonian sandstones and shales. Within these layers, we find abundant evidence of the flourishing terrestrial life, including the fossilized remains of Archaeopteryx trees and early fish, providing direct insights into the evolving biosphere that contended with the geological upheaval. Globally, remnants of large igneous provinces from the Devonian or their associated intrusions can still be found. While extensively eroded, the roots of these ancient basalt floods might be exposed in certain shield areas or uplifted terrains. Geologists painstakingly map these rock units, piecing together the original extent and volume of these immense eruptions. These are not always dramatic, towering volcanoes. Sometimes they manifest as extensive, dark, erosion-resistant sills and dikes, cutting through older rock formations, silent witnesses to a time when magma welled up from deep within the earth.
Beyond the visible rock formations, the Devonian also left a more subtle yet equally profound legacy: economic resources. The very anoxic events that decimated marine life also led to the preservation of vast quantities of organic matter in oxygen-depleted sediments. Over geological time, under immense heat and pressure, some of these organic-rich black shales transformed into significant reserves of oil and natural gas. Thus, the energy that powers our modern world is, in part, a direct inheritance from the turbulent Devonian, a period when a molten cataclysm ironically laid the groundwork for future energy reserves. A truly fascinating paradox. So, the next time you hike through ancient mountain ranges or even drive through a road cut exposing layers of rock, remember that you are walking through a landscape shaped by billions of years of Earth's dynamic history, including the fiery crucible of the Devonian. These rocks are not inert. They are vibrant archives, whispering tales of ancient oceans, nascent forests, and a planet in the throes of a grand planetary inferno, a testament to the enduring power of deep time.
Our understanding of the Devonian's molten cataclysm is built upon centuries of geological study, a fascinating journey of scientific discovery that itself blends adventure and intellectual drama. Imagine the early geologists, without modern technology, piecing together Earth's history from fragmented rock outcrops. How did they even define the Devonian period, and what were their initial insights into its fiery past? The Devonian period itself was first formally recognized and named in the 1830s by Roderick Murchison and Adam Sedgwick, based on studies of rock sequences in Devon, England, hence Devonian.
They observed distinctive fossil assemblages that were different from the underlying Silurian and overlying Carboniferous strata, indicating a distinct period of Earth's history. These early geologists were primarily focused on stratigraphy, the study of rock layers and their succession, and paleontology, using fossils to correlate rock units across different regions. Their pioneering work laid the groundwork for the geological timescale that we use today. The concept of deep time was revolutionary in itself. Before the 19th century, many believed Earth was only a few thousand years old. Geologists like James Hutton and Charles Lyell, through their observations of slow geological processes, began to articulate the immense antiquity of Earth. This intellectual shift was crucial for understanding events like large igneous province eruptions, which occur over millions of years. It moved geological thinking beyond a catastrophic short-term view to one of uniformitarianism, the idea that the same geological processes observed today operated in the past, albeit sometimes on different scales.
Early observations of volcanic rocks and their widespread distribution in certain regions would have provided initial clues about ancient magmatism. However, without precise dating techniques or a full understanding of plate tectonics, these observations would have been largely localized and disconnected. The link between volcanism and global climate change, or mass extinctions, would have been far beyond their grasp. It was through the cumulative work of generations of geologists, mapping, collecting fossils, and meticulously describing rock formations, that the larger picture began to emerge. The development of radiometric dating in the 20th century was a game-changer, providing the precision needed to accurately date ancient volcanic events and correlate them with the fossil record. This marked a shift from relative dating, which rocks are older or younger, to absolute dating, how many millions of years old. The historical context of Devonian geological studies is a testament to the scientific method itself, a slow, iterative process of observation, hypothesis, and refinement, where each generation builds upon the discoveries of its predecessors, gradually unveiling the dramatic secrets of Earth's ancient fiery epoch. It is a story of human curiosity, perseverance, and the relentless quest to understand our planet's profound history.
To truly grasp the scale of the Devonian's molten cataclysm, we must understand the very genesis of large igneous provinces, or LIPs. These are not merely big volcanoes, they are colossal geological features, representing the largest outpouring of magma on Earth, often dwarfing the combined output of all active volcanoes today. The formation of an LIP is a multi-stage process, beginning deep within the Earth's mantle and culminating in basaltic floods that reshape continents. The prevailing scientific theory attributes most LIPs to mantle plumes. Imagine a thermal anomaly, a blob of superheated rock originating from the deep mantle, possibly even from the core mantle boundary, around 2,900 kilometers deep. This plume, being hotter and less dense than the surrounding mantle, slowly but relentlessly rises through convection. It's a process that takes tens of millions of years. As the plume head approaches the base of the lithosphere, Earth's rigid outer layer, it begins to mushroom out, spreading laterally beneath the crust. This spreading action, coupled with the intense heat, causes significant melting of the overlying mantle and, crucially, the lower crust. The melting process generates enormous volumes of basaltic magma. This magma is highly fluid and, under immense pressure, seeks pathways to the surface. Rather than erupting from a single central conduit like a stratovolcano, LIP magmas typically erupt through extensive networks of fissures and cracks in the crust. These are the fissure eruptions that lead to the characteristic basalt floods, where lava flows across vast plains, sometimes for hundreds of kilometers, creating layer upon layer of solidified rock. The volume of magma erupted during a major LIP event
can range from hundreds of thousands to several million cubic kilometers. Think of it, a volume of rock equivalent to a small continent being extruded onto the surface.
The ascent of the mantle plume can also cause the overlying crust to dome upwards and undergo rifting, eventually leading to continental breakup. The North Atlantic igneous province, for example, is linked to the opening of the Atlantic Ocean. While the Devonian LIPs are older and less well preserved, the geological principles remain the same. The immense volumes of magma, the widespread nature of the eruptions, and the direct link to deep Earth processes distinguish LIPs from typical volcanic activity. The formation of these features is a direct consequence of Earth's internal heat engine, a powerful reminder of the planet's dynamic and often violent geological past, a past that included the ancient fiery epoch of the Devonian. The immediate aftermath of a large igneous province eruption during the Devonian's molten cataclysm was not just the flow of lava, but the expulsion of staggering quantities of gas into the atmosphere. This volcanic outgassing fundamentally reshaped the planet's atmospheric chemistry, triggering a cascade of environmental crises. Let's delve deeper into the specific gases released and their complex, often contradictory impacts. The primary greenhouse gases released are carbon dioxide, CO2, and methane, CH4. Carbon dioxide is a direct product of magma degassing, while methane can be generated by the thermal decomposition of organic-rich sediments or by methanogenic microbes in warm anoxic environments, which would have been abundant. The continuous injection of these gases over geological timescales would have caused significant and sustained global warming. This wasn't a short-term blip, it was a long-term perturbation of Earth's climate system, leading to warmer oceans, altered precipitation patterns, and the melting of any existing polar ice, though the Devonian was largely ice-free.
However, not all volcanic gases contribute to warming. Sulfur dioxide, or SO2, is another major component of volcanic emissions. When SO2 reacts with water vapor in the atmosphere, it forms tiny sulfuric acid aerosols. These aerosols are highly refractive and can scatter incoming solar radiation back into space, causing a temporary cooling effect. This is why large, explosive eruptions today, like Mount Pinatubo, can cause a slight short-term drop in global temperatures. But in the context of sustained LIP eruptions, the balance is crucial. While short-term cooling might occur, the sheer volume of CO2 released over millions of years would ultimately overwhelm any temporary cooling from SO2, leading to net warming. Other harmful gases include halogens like chlorine and fluorine, which can destroy ozone in the stratosphere, potentially increasing harmful UV radiation reaching the surface. Hydrogen sulfide, or H2S, a highly toxic gas, can also be released, contributing to atmospheric pollution and, when dissolved in water, further exacerbating anoxic conditions in the oceans. The precise cocktail of gases released depends on the magma composition and the style of eruption, adding complexity to reconstructing ancient atmospheric conditions. Scientists use a combination of geochemical models, isotopic analysis of ancient rocks, and proxies like the stomatal index of fossil plants to reconstruct the atmospheric composition during the Devonian. These lines of evidence consistently point to significant perturbations of Earth's atmosphere during periods of intense volcanism, transforming the sky from a familiar blue to a potentially hazy, often acidic and warming envelope. This complex interplay of gases highlights how the molten cataclysm wasn't just about lava, it was about the fundamental chemical transformation of the very air that life breathed.
Let's dive deeper into the fascinating lives of two iconic groups of organisms that faced the Devonian's molten cataclysm: the ancient coral reefs and the ubiquitous trilobites. Their stories are intimately woven into the narrative of Devonian life, from their initial flourishing to their eventual decline in the face of planetary stress. Devonian coral reefs. As mentioned earlier, these were not modern coral reefs. They were primarily built by tabulate corals,
colonial organisms forming honeycomb-like structures, and rugose corals, solitary or colonial corals with distinct growth rings, alongside stromatoporoids, extinct sponge-like organisms that formed massive layered structures. These organisms, particularly the stromatoporoids, were the dominant reef builders of the early and middle Paleozoic. They created vast, intricate bioherms and biostromes, ancient underwater cities that supported an incredible diversity of other marine life. Think of them as the biodiversity hotspots of their time, thriving in warm, shallow, sunlit waters. The fossil record of these ancient reefs is extensive, particularly in regions like the Great Lakes Basin in North America and parts of Europe, allowing paleontologists to study their growth patterns, ecological structure, and the myriad of organisms that inhabited them. The scale of these ancient reefs speaks to a highly productive marine environment for much of the Devonian. However, these complex ecosystems were inherently vulnerable to the geological upheaval. Their calcifying skeletons were susceptible to ocean acidification caused by volcanic CO2. Their reliance on clear, oxygenated waters meant they were highly impacted by increased turbidity from volcanic ash and, critically, by widespread ocean anoxia. The fossil record clearly shows a dramatic reduction in reef diversity and extent, and even total collapse in many regions, coinciding with the late Devonian extinction events. The disappearance of many of these reef-building groups marks a significant turning point in marine ecology, as it would be millions of years before similar large-scale reef systems would fully recover. Trilobites. These iconic arthropods were ubiquitous in Paleozoic seas, and the Devonian saw them continue their impressive evolutionary journey. From their early Cambrian origins, trilobites diversified into a stunning array of forms, occupying diverse ecological niches from bottom-dwelling scavengers to active predators. Devonian trilobites exhibit an astonishing range of bizarre and beautiful morphologies, including elaborate spines, strange headgear, and even eyes perched on stalks. Examples like Phacops, with its distinctive large eyes, are commonly found in Devonian strata. Their widespread distribution and rapid evolution make them excellent index fossils, fossils that are characteristic of a particular geological period, and thus useful for dating and correlating rock layers.
Like the corals, trilobites were profoundly affected by the molten cataclysm. While some lineages survived, the late Devonian extinction events caused a significant reduction in trilobite diversity. Many families and genera disappeared, never to return. Their extinction patterns, visible in the fossil record, provide direct evidence of the severity of the environmental changes. By studying the presence and absence of different trilobite species across stratigraphic boundaries, paleontologists can pinpoint the timing and severity of biotic crises, often correlating these with the geochemical signatures of volcanic events and anoxic conditions. The stories of Devonian coral reefs and trilobites are poignant reminders of life's intricate dance with planetary forces. They represent the vibrant life that flourished before and was profoundly impacted by the ancient fiery epoch, their fossilized remains serving as silent witnesses to a world dramatically reshaped by fire and water. While we emphasize the triumphs of radiometric dating in understanding the Devonian's molten cataclysm, it's crucial to acknowledge the persistent challenges in dating volcanic events that are hundreds of millions of years old. This is where the geochronologist's work becomes as much an art as a science, requiring meticulous technique, careful interpretation, and a deep understanding of geological processes. One of the foremost challenges is preservation. Volcanic rocks, especially those erupted as basalt floods, are often exposed to intense weathering and erosion over geological timescales. This can alter their mineralogy, introduce contaminants, or reset the isotopic clocks. Imagine trying to date an ancient manuscript that has been exposed to the elements for centuries. Crucial information might be lost or obscured. Geochronologists must seek out the most pristine samples, often from deep drill cores or freshly exposed outcrops, where alteration is minimized.
Contamination is another significant hurdle. During eruption, magma can incorporate older crustal rocks, leading to mixed isotopic signals. Conversely, younger groundwater flowing through fractures can introduce modern isotopes. Distinguishing between primary magmatic minerals and later alterations or contaminants requires sophisticated analytical techniques and careful sample preparation. For instance, tiny zircons, highly resistant minerals that often contain uranium, are a preferred target for UPB dating because they are durable and tend to retain their original isotopic signature even under adverse conditions. Extracting and analyzing these microscopic crystals is a painstaking process. Furthermore, accurately correlating dates from different locations to a single, massive, large igneous province event requires robust evidence. A single eruption might leave deposits across vast distances, but ensuring that different outcrops belong to the same magmatic pulse rather than separate localized events is complex. This often involves detailed geochemical analysis, looking for unique chemical fingerprints in the rocks that link them to a common magmatic source. Paleomagnetism, the study of Earth's ancient magnetic field recorded in rocks, can also help. If distinct lava flows show similar magnetic orientations, it can suggest they were erupted within a short geological time frame. The long half-lives of the isotopes used for dating ancient rocks also introduce inherent uncertainties. While these isotopes are ideal for deep time, the sheer magnitude of the decay period means that small analytical errors can translate into significant age uncertainties, sometimes in the millions of years. This means that precisely correlating a volcanic pulse to a specific extinction event, which might have occurred over thousands or tens of thousands of years, requires exceptional precision. The constant drive for higher precision and new analytical techniques defines the cutting edge of geochronology. The work is laborious, often frustrating, but each successful date is a triumph, illuminating another piece of Earth's ancient fiery epic and deepening our understanding of its profound impact. Our exploration of the Devonian's molten cataclysm isn't just about Earth's past. It offers fascinating astrobiological parallels, prompting us to consider the potential for life in similar extreme volcanic environments elsewhere in the universe. If life could survive and even thrive on a volcanic Earth 400 million years ago, what does that imply for the habitability of other planets or moons that might be experiencing intense volcanism today? The key lies in extremophiles, organisms that thrive in conditions considered hostile to most life on Earth. We know from modern research that diverse microbial communities flourish in extreme environments, many of which are volcanically active. Think of the deep-sea hydrothermal vents, often called black smokers, where superheated, mineral-rich fluids spew from cracks in the seafloor. Here, life thrives in perpetual darkness, at crushing pressures and scalding temperatures, deriving energy not from sunlight but from chemosynthesis, using chemical reactions with sulfur, methane, and other compounds. These are essentially mini-volcanic ecosystems. On land, volcanic hot springs, fumaroles, and geysers host a variety of extremophilic bacteria and archaea, adapted to high temperatures, acidity, and toxic chemical compounds. Some can even survive in conditions that mimic early Earth, where oxygen was scarce and volcanic activity rampant. If such life could find a foothold and persist in Earth's ancient fiery epoch, driven by massive large igneous province eruptions and associated outgassing, it suggests that similar planetary conditions might not be prohibitive for the emergence or sustenance of microbial life on other celestial bodies. Consider Europa, Jupiter's icy moon, which is thought to harbor a vast subsurface ocean warmed by tidal forces and potentially harboring hydrothermal vents. Or Enceladus, Saturn's moon, which periodically erupts plumes of water vapor and organic molecules, hinting at a subsurface ocean with hydrothermal activity. Even Mars, with its extensive history of volcanism, could have harbored life in subsurface environments warmed by ancient magmatic activity, shielded from the harsh surface radiation. The discovery of extremophiles on Earth has expanded our definition of habitability, pushing the boundaries of where life can exist. The Devonian provides a powerful Earth-based analog for these astrobiological questions. It demonstrates that life, at its most fundamental level, can adapt to and even harness the energy from extreme geological upheavals. It sparks our imagination, prompting us to wonder, could the fiery infernos of distant exoplanets or moons be teeming with their own unique forms of extremophilic life, silently thriving in conditions that we once considered utterly inhospitable? The discovery of extremophiles on Earth has expanded our definition of habitability, pushing the boundaries of where life can exist.
Our journey through the Devonian's molten cataclysm reveals Earth's immense geological power and its capacity for self-transformation. This perspective naturally leads to a series of profound ethical questions about humanity's impact on Earth's geology in the modern era. While we cannot trigger a large igneous province eruption, our actions, particularly our fossil fuel consumption, are undeniably pushing Earth's systems towards conditions reminiscent of ancient planetary crises. The Devonian showcased how massive injections of CO2 from volcanic outgassing led to global warming, ocean anoxia, and acidification. Today, human industrial activity is releasing carbon dioxide into the atmosphere at a rate unprecedented in geological history, far exceeding natural volcanic emissions. While the source of the carbon is different, volcanic versus combustion of fossil fuels, the effect on the atmosphere and oceans is strikingly similar. We are, in essence, conducting a massive, uncontrolled geological experiment on our own planet. This raises a fundamental ethical dilemma. What responsibility do we bear for consciously altering the very geological processes that have shaped life for billions of years? Consider the concept of the Anthropocene, a proposed new geological epoch characterized by dominant human influence on Earth's geology and ecosystems. While the Devonian saw geological upheaval driven by internal planetary forces, the Anthropocene is defined by an external force, humanity. We are altering sedimentation rates, changing atmospheric composition, driving extinctions, and even affecting the chemistry of the oceans. Are we, inadvertently, creating conditions that mirror the cataclysmic events of the deep past, but at an accelerated rate?
Furthermore, our extraction of geological resources, from fossil fuels to rare earth minerals, is profoundly altering Earth's crust. We are essentially mining the planet's deep history, often without fully understanding the long-term environmental consequences. This raises questions about intergenerational equity. What kind of geological and environmental legacy are we leaving for future generations? Are we simply consuming the planet's capital, or are we striving for a sustainable interaction with its immense, yet finite resources? The philosophical implication here is that understanding Earth's deep time, its periods of molten fury and subsequent recoveries, should foster a sense of humility and responsibility. It shows us that Earth is a dynamic system, capable of dramatic shifts. While human geological impact is minuscule compared to a mantle plume, our rate of change is phenomenal. The ethical imperative arising from studying the Devonian is not to despair, but to recognize our unique geological agency and to act with foresight and care, aiming to steer our planetary journey towards a more stable future, rather than inadvertently mimicking the destructive forces of the ancient fiery epoch. Despite the remarkable scientific advancements in understanding the Devonian's molten cataclysm, it's crucial to acknowledge the silences in the record. the vast unknowns and lingering questions that continue to challenge geologists and paleontologists. Science is a continuous process of discovery, and for every mystery solved, new ones often emerge. What don't we know yet about this ancient fiery epoch, and what are the frontiers of research? One significant unknown is the precise spatial and temporal extent of all Devonian large igneous provinces, or LIPs. While the Velui traps are relatively well studied, there might be other, less recognized or deeply buried LIPs that contributed to the global magmatic pulse. Erosion, burial under younger sediments, and subsequent tectonic deformation make it incredibly difficult to map the full extent of these ancient basalt floods. Locating and precisely dating these elusive magmatic bodies is a continuous challenge, often requiring extensive geological surveying, drilling, and sophisticated geophysical imaging techniques. Another major area of uncertainty lies in the exact mechanisms and feedbacks between volcanism, climate, and extinction. While the correlation between Devonian volcanism, carbon isotope anomalies, warming, anoxia, and extinction is strong, the precise causal pathways and the relative importance of different stressors remain subjects of active debate. For instance, were the anoxic events primarily driven by warming-induced stratification, or did enhanced nutrient runoff from weathered volcanic rocks also play a significant role? How quickly did the atmosphere and oceans respond to massive gas injections? These are complex, non-linear systems, and disentangling the various feedback loops requires highly sophisticated climate and Earth system models. Furthermore, the biological response to these environmental changes is not fully understood. While we see broad patterns of extinction, the differential survival of various groups and the long-term evolutionary consequences are still being investigated. Why did some lineages survive the molten cataclysm while others perished? What were the specific physiological adaptations that allowed certain organisms to cope with ocean deoxygenation or acidification? The fossil record, while rich, is incomplete, and many crucial details about ancient ecosystems remain elusive.
Finally, the deep mantle processes that drive mantle plumes themselves are still poorly understood. What causes a plume to initiate? Are they linked to specific areas of the core mantle boundary? How do they interact with overlying plate tectonics? These are fundamental questions in solid Earth geophysics, and unraveling them could provide deeper insights into the ultimate drivers of past and future geological upheavals. The silences in the record are not a sign of scientific failure, but rather a testament to the immense complexity of Earth's history and an invitation for future generations of scientists to continue the daring journey of discovery into our planet's fiery past. Our journey through the Devonian's molten cataclysm compels us to confront a profound philosophical legacy, the necessity of embracing Earth's volatile narrative as integral to its story and our own. For centuries, humanity has often sought stability, predictability, and a sense of permanence in the natural world. Yet the deep time perspective, particularly lessons from the ancient fiery epoch of the Devonian, shatters this illusion, revealing a planet that is constantly in flux, shaped by forces of staggering power. This acceptance of Earth's inherent volatility is not a call to despair, but rather an invitation to a deeper understanding and a more profound respect for our home planet. It highlights that the very conditions that allowed complex life to evolve, the shifting continents, the cycles of volcanism, the dynamic climate, are also the forces that have periodically pushed life to its brink. The geological upheaval of the Devonian was not an anomaly. It was part of the planet's normal, albeit often dramatic, operating mode. Embracing this volatile narrative means recognizing that Earth is not a static backdrop for human history, but an active, living entity with its own rhythms and cycles. It means appreciating the immense timescales over which geological processes unfold, and understanding that what we perceive as stable or normal is often just a fleeting moment in Earth's billions of years of history. The rise and fall of supercontinents, the ebb and flow of ice ages, the bursts of molten fury from mantle plumes. These are the grand narratives that truly define our planet.
This philosophical shift also encourages us to rethink our relationship with natural disasters. While we understandably seek to mitigate their impact on human lives, understanding their deep geological roots allows us to see them not as arbitrary misfortunes, but as expressions of the planet's ongoing dynamism. The Devonian reminds us that events like massive volcanic eruptions or climate shifts are inherent parts of Earth's story, and life has, for billions of years, found ways to adapt, evolve, and persist amidst them. Ultimately, by embracing Earth's volatile narrative, we gain a more nuanced and realistic perspective on our place in the cosmos. It grounds us in the profound interconnectedness of geological processes and biological evolution, fostering a sense of awe and responsibility. The Devonian's molten cataclysm, therefore, is not just a scientific curiosity. It is a powerful philosophical lesson, urging us to listen to the whispers of deep time and to appreciate the dramatic, ever-changing story of our remarkable home, the one truly fiery crucible that forged life's destiny.
While the Devonian period hosted multiple instances of significant volcanism, one of the most compelling examples of a large igneous province with potential Devonian ties is the Viliui Traps in Siberia. Though parts of the Viliui Traps are primarily recognized for their later Permian-Triassic activity, scientific investigations suggest a significant, though less understood, precursor magmatic pulse that likely contributed to the broader Devonian's molten cataclysm. Understanding the formation of the Viliui Traps offers a detailed case study into the mechanics and scale of these ancient basalt floods. The Viliui Traps represent a vast area of flood basalts and associated intrusive rocks, like sills and dikes, in the Siberian Craton. Their formation, like many LIPs, is generally attributed to the ascent of a colossal mantle plume. Imagine a super-hot column of rock rising from deep within the Earth, impacting the base of the ancient Siberian continental plate. As this plume head mushroomed out beneath the crust, it would have caused extensive melting, generating enormous volumes of highly fluid basaltic magma. This magma then exploited existing weaknesses and fractures in the overlying crust, erupting onto the surface through extensive fissure vents. The evidence for Devonian magmatism in the Viliui region is often more subtle than the later more voluminous Permian-Triassic events. It typically comes from the dating of specific intrusive bodies, like dolerite dikes and sills that cut through older Devonian sedimentary rocks, or from distinct geochemical signatures found within certain volcanic sequences. While perhaps not as massive in individual eruption pulses as the later events, the cumulative effect of these Devonian-aged intrusions and extrusions would have contributed substantially to the overall geological upheaval of the period. This earlier phase of magnetism might represent the initial stages of the same mantle plume that would later culminate in the immense Permian-Triassic eruptions.
The sheer scale of the Viliui Traps, even considering their Devonian precursors, is staggering. When fully formed, these flood basalts covered hundreds of thousands of square kilometers, with an estimated volume of hundreds of thousands to 1,000,000 cubic kilometers of basalt. Such immense eruptions don't just transform the landscape. They release enormous quantities of volcanic gases, CO2, SO2, halogens, into the atmosphere. This outgassing, even from the earlier Devonian phases of the Viliui system, would have significantly perturbed Earth's climate and ocean chemistry, contributing to the global warming and anoxic events that characterize the ancient fiery epoch. The study of the Viliui Traps is an ongoing effort, with scientists continually refining the chronology and volume of its various magmatic phases. By precisely dating these ancient events, researchers can better correlate them with the biological and environmental changes observed in the Devonian rock record, strengthening the link between large igneous province formation and major planetary crises. The Volui traps stand as a powerful testament to the long-term, devastating power of Earth's internal engine and its profound influence on the evolution of life.
We've explored the primary gases involved in volcanic outgassing during the Devonian's molten cataclysm: carbon dioxide, sulfur dioxide, and methane. But to truly appreciate the complexity of how Earth's atmosphere was reshaped, we need to go beyond the basics and consider the intricate chemical reactions and feedback loops that would have occurred. This wasn't just a simple addition of gases, it was a fundamental re-engineering of the atmosphere. Consider the role of halogen gases like chlorine, Cl, and fluorine, F. While less voluminous than CO2 or SO2, these gases can have disproportionately powerful impacts on atmospheric chemistry. In the stratosphere, chlorine compounds can catalytically destroy ozone, O3, the vital layer that shields Earth's surface from harmful ultraviolet, UV, radiation. A significant reduction in the ozone layer during the Devonian would have subjected early terrestrial life, already struggling to adapt to land, to increased UV stress. This could have damaged DNA, inhibited photosynthesis, and limited the spread of sensitive organisms, especially in regions with thinner ozone layers. Furthermore, the increased acidity from acid rain, formed from SO2, would have accelerated the weathering of rocks on land. This might seem beneficial, as weathering consumes CO2 from the atmosphere over geological timescales. However, this process also releases nutrients like phosphorus and iron into rivers, which then flow into the oceans. A sudden influx of these nutrients can trigger massive algal blooms in marine environments. When these blooms die and sink, their decomposition consumes vast amounts of oxygen, further exacerbating ocean anoxia and potentially leading to the formation of widespread black shales. This is a crucial feedback loop. Volcanism drives weathering, which provides nutrients, which enhances anoxia, leading to more organic carbon burial, which can over time affect the global carbon cycle. The exact mix of gases and their subsequent reactions would have been influenced by several factors, including the composition of the erupted magma, the temperature of the eruptions, and the existing atmospheric conditions. For instance, the presence of vast early forests on land, themselves drawing down CO2 through photosynthesis, would have created a complex interplay with volcanic emissions. Were these forests resilient enough to counteract some of the volcanic CO2? Or were they overwhelmed by the sheer volume of emissions and the effects of acid rain?
Reconstructing these complex interactions for the Devonian involves sophisticated geochemical modeling, combining data from ancient rocks, fossils, and modern analogs. It highlights that the Devonian's molten cataclysm was not just a singular event, but a prolonged period of cascading environmental changes where the unseen architects of atmospheric chemistry played a dramatic and often devastating role in shaping Earth's biosphere. The Devonian period truly earned its moniker as the Age of Fishes, witnessing an unparalleled diversification that transformed marine ecosystems. But this incredible fish explosion was not an interrupted ascent. It was profoundly impacted and ultimately truncated by the molten cataclysm that gripped the planet. Let's explore the marvel of Devonian fish evolution and the dramatic interruption it faced. Before the Devonian, fish were relatively simple, jawless forms, resembling modern lampreys. The Devonian, however, saw the rapid evolution of jaws, paired fins, and scales, leading to the emergence of highly efficient predators and diverse ecological roles. Placoderms, or plate-skinned fish, were among the earliest jawed vertebrates and dominated the early Devonian. These armored fish, ranging from small, bottom-dwelling forms to the colossal apex predator Dunkleosteus, were incredibly successful. Their heavy bony armor protected them, and their powerful jaws allowed them to exploit new food sources. Alongside placoderms, the Devonian also saw the rise of the first cartilaginous fish, the ancestors of modern sharks and rays.
While often less abundant in the fossil record due to their cartilaginous skeletons not preserving as well as bone, their presence indicates a growing diversity of predatory roles. Most significantly, the bony fish, Osteichthyes, made their debut, splitting into two major lineages, the ray-finned fish, Actinopterygii, which would eventually dominate modern aquatic environments, and the lobe-finned fish, Sarcopterygii. The lobe-finned fish are particularly significant as they include the ancestors of all tetrapods, making the Devonian a pivotal time for the transition of vertebrates from water to land.
This incredible evolutionary burst was largely driven by new ecological opportunities and innovative adaptations. However, this vibrant marine world faced an existential threat from the geological upheaval. The anoxic events and ocean acidification caused by intense volcanic outgassing proved to be devastating. The fossil record clearly shows that many Devonian fish lineages, particularly the placoderms, experienced significant declines or went extinct during the late Devonian extinction events. While the exact causes of individual species demise are complex, the overall pattern points to widespread environmental stress. The survivors of the molten cataclysm were often the more adaptable and mobile forms, particularly certain groups of bony fish, which would go on to diversify spectacularly in the Carboniferous and beyond. The Devonian fish explosion, therefore, serves as a powerful testament to both life's remarkable capacity for innovation and its profound vulnerability to drastic planetary change. It highlights a period where the very architect of life, evolution, was profoundly shaped by the unseen hand of a fiery crucible. The ability to piece together the narrative of the Devonian's molten cataclysm with increasing precision is thanks in large part to the radiometric revolution in geological dating. While we touched on the challenges, let's explore how this technology, developed over the last century, transformed our understanding of deep time and the timing of large igneous province eruptions. Before radiometric dating, geologists relied on relative dating, determining the sequence of events without assigning absolute ages. This involved principles like superposition, older layers are at the bottom, and fossil correlation. While crucial for establishing the geological timescale, it couldn't tell us exactly how old the Devonian period was or how long the volcanic events lasted. The advent of radiometric dating provided the much-needed absolute chronology. The breakthrough came with the understanding of radioactive decay. Elements like uranium, potassium, and rubidium have unstable isotopes that decay into stable daughter isotopes at predictable, constant rates. This decay rate is measured by the half-life, the time it takes for half of the parent isotope to decay into a daughter isotope. For geological timescales, isotopes with very long half-lives are used, such as uranium-lead, uranium-thorium, and argon-argon. The UP system, particularly using the mineral zircon, has become the gold standard for dating ancient volcanic events with high precision. Zircons are incredibly durable minerals that crystallize directly from magma and incorporate uranium but strongly exclude lead. This means any lead found within a pristine zircon crystal must be the result of radioactive decay from uranium. By carefully analyzing the ratios of different uranium and lead isotopes using highly sensitive mass spectrometers, geochronologists can determine the precise age of crystallization, often with uncertainties of less than 1 million years, or even tens of thousands of years for younger, well-preserved samples.
The application of these techniques to Devonian volcanic rocks and associated ash layers, which can be preserved in sedimentary sequences, has revolutionized our understanding of the timing of the ancient fiery epoch. For instance, precisely dated ash beds within sedimentary sequences can provide absolute age constraints for fossil horizons and carbon isotope anomalies, allowing scientists to establish direct correlations between volcanic events and environmental changes. This ability to pinpoint events in deep time with such accuracy has allowed scientists to move beyond mere correlation and to propose robust causal links between the Devonian's molten cataclysm and the dramatic transformations in Earth's climate and biosphere. The radiometric revolution has truly given geologists a working clock to decipher the vast, silent narrative of our planet's fiery past. Our journey into the Devonian's molten cataclysm serves as a potent case study for astrobiological implications, specifically concerning the habitability of volcanic worlds beyond Earth. If Earth, a planet teeming with complex life, endured and was fundamentally shaped by periods of intense volcanism, what does this tell us about the potential for life on exoplanets or moons that might be far more volcanically active than our current Earth? Consider the sheer energy provided by volcanism. On Earth, hydrothermal vents at the bottom of the ocean, fueled by geothermal energy, support thriving ecosystems entirely independent of sunlight. These are deep-sea ecosystems driven by chemosynthesis, where microbes derive energy from the chemical reactions of minerals and gases spewing from volcanic vents. If such ecosystems could persist and evolve on ancient Earth during its fiery epoch, it dramatically broadens our search for life beyond our solar system.
Take, for example, the concept of a lava world or a hot super-Earth. While their surfaces might be molten, their deeper interiors could still harbor zones where water exists in a supercritical state, or where pockets of cooler, chemically active environments provide niches for specialized life. The Devonian reminds us that life's tenacity knows few bounds when given the right chemical ingredients and a persistent energy source, even amidst a molten cataclysm. Furthermore, volcanic outgassing, while potentially destructive, is also crucial for initiating and sustaining a planetary atmosphere over geological timescales. Without volcanism, planets would gradually lose their atmospheres to space. So, paradoxically, the very forces that can drive environmental crises are also essential for maintaining the conditions necessary for life. The Devonian highlights this dual role, the creator and destroyer. Therefore, when searching for life on other planets, astronomers and astrobiologists are not just looking for Earth-like conditions in the present, but also for worlds with dynamic geological histories, including periods of intense volcanism. The ancient fiery epoch of our own planet provides a tantalizing template for what a habitable yet volatile world might look like across the vastness of the cosmos.
The emergence of early terrestrial ecosystems during the Devonian was a monumental evolutionary leap, but one that occurred against the dramatic backdrop of the molten cataclysm. Among the most significant developments was the appearance of the first tetrapods, four-limbed vertebrates that are the ancestors of all amphibians, reptiles, birds, and mammals. How did these pioneers of land cope with, and perhaps even benefit from, a volcanic Earth? The transition from water to land was not a single event, but a gradual process driven by a complex interplay of environmental pressures and evolutionary innovations. Lobe-finned fish, like Tiktaalik, though slightly older than the main Devonian period, representing a key transitional fossil, possessed robust fins that could support their weight in shallow water and rudimentary lungs for air breathing. As oxygen levels in aquatic environments fluctuated, potentially exacerbated by ocean anoxia during volcanic episodes, the ability to gulp air would have become a significant advantage, allowing these fish to survive in oxygen-depleted ponds or to move between bodies of water. The first true tetrapods, such as Ichthyostega and Acanthostega, appeared in the late Devonian. These creatures still retained many fish-like characteristics, but possessed well-developed limbs and digits, capable of supporting their bodies on land. Their environments were likely marginal, shallow, swampy areas, perhaps frequently inundated and then exposed as water levels changed.
These fluctuating conditions, potentially intensified by the climatic instability associated with volcanic outgassing, could have provided a powerful selective pressure for terrestrial adaptations.
Imagine a Devonian swamp. The air might be humid, potentially hazy with volcanic aerosols, and the water warm and oxygen poor due to periods of anoxia. A fish that could temporarily move onto a muddy bank to escape suffocating conditions or to seek out new food sources would have had a survival advantage. Over millions of years, these tentative steps onto land, perhaps driven by escape from competition or predation in the water, or the lure of untapped terrestrial food resources like arthropods, led to the full terrestrialization of vertebrates. While the late Devonian extinction events undoubtedly impacted terrestrial ecosystems, those lineages that had already made significant strides onto land might have been somewhat buffered from the worst of the marine crises. The very challenges posed by a fiery crucible, fluctuating water levels, oxygen stress, altered landscapes, may have inadvertently forged the adaptations necessary for vertebrates to truly conquer a new frontier. The story of the first tetrapods is a profound testament to life's adaptability, transforming planetary turmoil into an evolutionary opportunity.
Our journey through the Devonian's molten cataclysm benefits immensely from comparative analysis with other volcanic periods in Earth's history, especially those linked to major environmental shifts and mass extinctions. By examining the similarities and differences, we gain a deeper understanding of the recurring patterns of Earth's geological rhythm and the unique aspects of the ancient fiery epoch. The most direct comparisons are often made with the Siberian traps, Permian-Triassic extinction, and the Deccan traps, Cretaceous-Paleogene extinction. The similarity is striking in the overall mechanism. Massive, large, igneous province eruptions, driven by mantle plumes, lead to colossal volcanic outgassing of greenhouse gases, CO2, CH4, and climate-altering aerosols, SO2. This results in global warming, ocean anoxia, ocean acidification, and sometimes ozone depletion, culminating in widespread biodiversity loss. This recurring sequence suggests a fundamental vulnerability of Earth's biosphere to sustained, large-scale magmatic events. It's a recurring theme in Earth's volatile narrative. However, there are also crucial differences. The magnitude and timing of the eruptions vary. The Siberian traps, for instance, are widely considered the most voluminous and rapid LIP event in Earth's history, explaining the severity of the Permian-Triassic extinction. While Devonian LIPs were significant, their exact cumulative volume and eruption rates are still being refined, and some suggest they were perhaps less concentrated in time than the Siberian traps. The Devonian magmatism might have been a more protracted, multi-stage process, leading to pulses of environmental stress rather than a single hypercataclysmic event. Another key difference lies in the state of the biosphere at the time of these events. The Devonian extinction impacted nascent terrestrial ecosystems and marine life that was rapidly diversifying. The Permian-Triassic extinction, conversely, hit fully established, complex terrestrial and marine biomes. The evolutionary consequences, therefore, differed. The Devonian paved the way for the dominance of bony fish and the continued expansion of forests, while the Permian-Triassic led to the rise of dinosaurs and mammals. Furthermore, the tectonic setting can vary. While all LIPs are linked to mantle plumes, their interaction with existing plate boundaries and continental configurations can differ. The Devonian saw active continental collisions and nascent rifting, while later LIPs might have occurred in different tectonic contexts. Understanding these nuances helps scientists refine their models of plume dynamics and their crustal expression. In summary, the comparative analysis reinforces the idea that molten cataclysms have been a recurring, powerful architect of life's history on Earth. Each event, while sharing fundamental mechanisms, played out on a unique stage, with unique actors, the evolving biosphere, leading to distinct,
yet equally dramatic chapters in Earth's ever-unfolding story. The Devonian, therefore, is not just an isolated event, it's a vital piece in the grand puzzle of planetary transformation.
As our understanding of the Devonian's molten cataclysm continues to evolve, so too do the future geological methods that will allow us to unravel its remaining mysteries. The scientific toolkit for peering back 400 million years is constantly being refined, promising even more precise and comprehensive insights into this ancient fiery epoch. One significant area of advancement is high-resolution geochronology. While we already use techniques like UP dating of zircons, the precision continues to improve. Future methods will aim to push the boundaries of accuracy even further, allowing for sub-million-year or even sub-100,000-year resolution for ancient events. This will be critical for precisely correlating volcanic pulses with specific short-lived environmental events or extinction intervals. New isotopic systems or refinements to existing ones will also contribute to this quest for greater chronological precision. Another frontier lies in advanced geochemical analysis of ancient rocks. The development of techniques that can analyze ultra-trace elements and exotic isotopes in volcanic rocks will provide more detailed fingerprints of their mantle sources and their interaction with the crust. This will allow scientists to better understand the plumbing systems of large igneous provinces, the specific types of magmas erupted, and the volatile content, gases, locked within them. For instance, analyzing the isotopic composition of sulfur or mercury in sedimentary rocks might provide direct evidence of volcanic outgassing even in areas where the volcanic rocks themselves are poorly preserved. Paleomagnetic studies will also become increasingly sophisticated. By studying the remnant magnetism in Devonian rocks, scientists can reconstruct the ancient positions of continents with greater accuracy, providing a more precise tectonic framework for understanding the distribution and drivers of volcanism. New techniques in magnetostratigraphy, correlating magnetic reversals in rock layers, could also provide additional chronological control. Perhaps most exciting are advancements in seismic imaging and deep drilling. Seismic waves, generated by artificial sources or earthquakes, can be used to create 3D images of Earth's subsurface. Applying advanced seismic tomography to ancient cratons and sedimentary basins could help locate or bury Devonian LIPs and their feeding systems, providing unprecedented views of their architecture. Deep drilling projects, where cores are extracted from kilometers beneath the surface, offer pristine, unaltered samples of Devonian rocks that are invaluable for dating and geochemical analysis, bypassing the challenges of surface weathering.
Finally, the increasing power of computational modeling will be transformative. Earth system models can simulate the complex interactions between volcanism, climate, ocean chemistry, and the biosphere with ever greater fidelity. These models can test different scenarios of volcanic outgassing and planetary response, allowing scientists to pinpoint the most likely drivers of Devonian environmental change. By combining these diverse, cutting-edge methods, future generations of geologists will continue to peel back the layers of time, revealing an even more detailed and dramatic narrative of the Devonian's molten cataclysm. Our journey through the Devonian's molten cataclysm offers some of the most compelling astrobiological parallels for the search for alien life. The discovery of extremophiles, life forms thriving in conditions once thought impossible, has revolutionized our understanding of planetary habitability. The Devonian, a period where Earth itself resembled a far more extreme world, underscores that life's tenacity and adaptability are far greater than we once imagined. Think about the conditions on a volcanically active early Earth, or a Devonian Earth gripped by molten cataclysms. High temperatures, acidic oceans, fluctuating oxygen levels, and pervasive toxic gases. Yet life persisted and diversified. This directly informs our approach to looking for life beyond Earth. We are no longer limited to searching for planets that are perfect Earth 2.0s with abundant liquid water, temperate climates, and oxygen-rich atmospheres.
The Devonian teaches us that life can find a foothold in far harsher, volcanically driven environments. Consider the subsurface oceans of icy moons like Europa and Enceladus in our own solar system. These moons are believed to harbor vast liquid water oceans beneath their icy shells, heated by tidal forces from their giant gas planet hosts. This internal heating could drive hydrothermal activity on their ocean floors, creating deep-sea volcanic vents similar to Earth's. If life on Devonian Earth could thrive in oxygen-poor, chemically active, and often warm environments, then these subsurface oceans fueled by internal geothermal energy become prime candidates for harboring microbial life even in the absence of sunlight.
Beyond our solar system, the countless exoplanets we are discovering offer an even wider range of possibilities. Many super-Earths, larger rocky planets, might have much thicker lithospheres and more intense internal heating, leading to sustained, powerful volcanism. If they possess atmospheres and liquid water, even if it's trapped in a subsurface ocean or existing as supercritical fluid, the lessons from the Devonian suggest that life could potentially evolve and persist there, perhaps as robust extremophiles adapted to these volcanic worlds. The key takeaway is that volcanism, while often associated with destruction, is also a fundamental driver of planetary evolution and a powerful energy source. It recycles nutrients, releases gases that form atmospheres, and provides heat that can sustain liquid water. The Devonian's ancient fiery epic reminds us that life and planetary turmoil are not mutually exclusive. Instead, Earth's turbulent past provides a powerful conceptual framework for expanding our search for life beyond our familiar blue planet, encouraging us to look for the subtle signs of life thriving amidst the geological upheaval of distant, volatile worlds.
Our exploration of the Devonian's molten cataclysm brings into sharp focus the profound ethical questions surrounding humanity's role as stewards of Earth in the modern era, often dubbed the Anthropocene. While we cannot unleash a large igneous province, our actions are undeniably impacting Earth's systems on a geological scale, raising concerns about the long-term consequences of our choices. The Devonian provides a powerful historical analog for the potential impacts of rapid climate change. The immense volcanic outgassing of CO2 led to global warming, ocean anoxia, and acidification, ultimately culminating in mass extinctions. Today, human industrial activity, primarily through the burning of fossil fuels, is releasing CO2 into the atmosphere at a rate that far outstrips natural geological processes. This rapid, human-induced greenhouse effect is fundamentally altering Earth's climate, ocean chemistry, and biodiversity, mirroring the effects of past molten cataclysms, albeit with a different origin. This places a unique ethical burden on humanity. Unlike the Devonian, where the geological upheaval was a purely natural planetary process, our current environmental changes are largely self-inflicted. We now possess the scientific understanding to comprehend these processes and the technological capacity to mitigate their worst effects. Therefore, the ethical imperative is clear. We have a responsibility to act. This responsibility extends not only to current generations, but also to future ones, ensuring that we do not leave them a planet irrevocably altered or diminished by our short-sightedness.
Stewardship in the Anthropocene means recognizing that we are not merely inhabitants of Earth, but now active geological agents. Our infrastructure, our cities, our agricultural lands, and our atmospheric emissions are leaving a distinct geological signature. The ethical challenge is to shift from an exploitative relationship with the planet to one of responsible guardianship. This involves transitioning to sustainable energy sources, developing circular economies, conserving biodiversity, and working collaboratively on a global scale to address shared environmental challenges. The philosophical reflection from the Devonian reinforces the interconnectedness of all Earth systems, geology, climate, and life. It teaches us that pushing one part of the system too far can have unforeseen and cascading consequences for the entire planet. The ethical lesson is one of humility and foresight. We must acknowledge the immense power of Earth's natural processes, learn from its deep history, and use our unique capacity for reason and innovation to ensure a more sustainable and harmonious future for both humanity and the remarkable planet we call home. The ancient fiery epoch is not just a warning, it's a powerful call to responsible action.
The Devonian's molten cataclysm is not merely a fascinating chapter from Earth's deep past. Its legacy of fire continues to shape our world today in profound, often unseen ways. The very foundations of our continents, the resources we extract, and even the fundamental patterns of life on Earth bear the indelible marks of this ancient fiery epoch. Firstly, the geological structures created by large igneous provinces and intense tectonic activity during the Devonian form part of the bedrock of our modern continents. While billions of years of erosion and subsequent geological events have modified them, the roots of these ancient magmatic events, or the sedimentary basins formed adjacent to them, are still present. These ancient rock formations tell a story of immense power, of continents tearing apart and colliding, and of Earth's crust being fundamentally re-engineered by internal forces. Geologists continue to map and study these Devonian rock units, using them as archives to understand the broader evolution of our planet. Secondly, the Devonian's environmental upheavals had a direct impact on the distribution of natural resources. As we discussed, the widespread anoxic events during periods of intense volcanism led to the burial and preservation of vast quantities of organic matter in oxygen-depleted sediments. Over millions of years, under immense heat and pressure, these organic-rich black shales transformed into significant oil and natural gas resources. So the very energy that powers our modern industrialized world is, in part, a direct inheritance from the turbulent Devonian, a period where catastrophic environmental conditions, ironically, created the conditions for future fossil fuel formation. This presents a complex irony. The legacy of an ancient environmental crisis now fuels our modern one. Beyond the physical geology and resources, the evolutionary consequences of the Devonian also resonate today. The survivors of the molten cataclysm were the lineages that proved most resilient and adaptable. The fish that diversified, and particularly the lobe-finned fish that gave rise to tetrapods, laid the groundwork for the entire terrestrial vertebrate lineage, including humans. The rise of Earth's first forests fundamentally altered global biogeochemical cycles, pulling CO2 from the atmosphere and enriching soils, setting the stage for more complex terrestrial ecosystems. The very fabric of biodiversity on Earth today is a product of these ancient evolutionary bottlenecks and subsequent radiations.
Therefore, the Devonian's molten cataclysm is not just a historical curiosity, it is a vital lens through which to understand the dynamic, interconnected nature of our planet. It shows us that deep time events have long, reverberating consequences that continue to influence the world we inhabit. By understanding the legacy of this fiery crucible, we gain a profound appreciation for Earth's immense power and the intricate web of life it has sustained throughout its dramatic, ever-unfolding story. Our journey through the Devonian's molten cataclysm has spanned hundreds of millions of years, exploring a period when Earth was transformed by intense volcanism and its profound consequences for life. Yet, as with all great scientific endeavors, the quest to unveil Earth's fiery past is a continuous and evolving one. We have answered many questions, but countless others remain, fueling the curiosity and dedication of generations of scientists. Every new fossil discovery, every precisely dated rock sample,
Every refinement in climate modeling adds another piece to this complex planetary puzzle. The frontiers of research are constantly expanding, pushing the boundaries of our understanding deeper into Earth's history and outward to other worlds. From microscopic zircons whispering ancient secrets to satellite imagery revealing the subtle scars of ancient basalt floods, the tools and techniques employed by geologists and paleontologists are becoming ever more sophisticated. This continuous quest is driven by an insatiable human desire to understand our origins. Where did we come from? How did life on Earth become so complex and diverse? What are the ultimate forces that shape our planet? The Devonian's molten cataclysm provides a powerful, dramatic answer to some of these questions, revealing how periods of intense geological upheaval have been fundamental architects of the world we know. It is a story of destruction and creation, of immense power and remarkable resilience, echoing across the vastness of deep time.
The narrative we have explored, of a planet in the throes of a fiery epic, of evolving life struggling against immense odds, of the intricate dance between Earth's interior and its surface environment, is a testament to the power of scientific inquiry. It shows how fragmented evidence, meticulously collected and interpreted, can reconstruct a coherent and compelling story of a lost world. This journey is not just for academics. It is for anyone who has ever gazed at a mountain, picked up a fossil, or simply wondered about the profound forces that shaped our home. So as we conclude this exploration, remember that Earth's history is far from static. It is a dynamic, living narrative, constantly being written by the forces deep within its core and the life that thrives upon its surface. The Devonian's molten cataclysm is a powerful chapter in that story, a vivid reminder that our planet is, and always has been, a world of immense power, constant change, and enduring mystery. The quest to understand it, therefore, is an endless and infinitely rewarding adventure.
Our journey through the 400 million years ago, when Earth became a volcanic inferno, has been a breathtaking expedition into one of our planet's most dramatic chapters. We embarked on a daring exploration of the Devonian period, unveiling a world where immense geological upheaval transformed Earth into a molten cataclysm. We've seen how colossal, large igneous provinces, driven by deep mantle plumes, erupted vast basalt floods, reshaping continents and pumping staggering volumes of gases into the atmosphere. This ancient fiery epoch didn't just alter landscapes, it profoundly re-engineered Earth's climate, triggering widespread global warming, suffocating ocean anoxia, and corrosive acidification. Yet, amidst this planetary turmoil, life found remarkable ways to persist and evolve. We witnessed the incredible fish explosion in the oceans and the pioneering steps of the first tetrapods onto land, their survival often forged in the crucible of environmental stress. The fossil record and intricate geochemical signatures, particularly carbon isotope anomalies, serve as our guides, revealing the undeniable links between volcanism, environmental collapse, and the late Devonian extinction events. We also considered the deep philosophical implications, seeing humanity's own impact on Earth through the lens of deep time, and pondered the astrobiological parallels that suggest life's enduring tenacity in volcanic environments across the cosmos. This exploration underscores a profound truth. Earth is a dynamic planet, constantly in motion, sculpted by forces of immense power. The Devonian serves as a vivid reminder that cataclysmic events are not mere anomalies, but integral parts of our planet's narrative, shaping the very course of life's evolution. Our understanding of this fiery past deepens our appreciation for the delicate balance that sustains life today, and highlights our profound connection to Earth's volatile history. The quest to unravel these ancient mysteries is a testament to human curiosity, a relentless pursuit of knowledge that bridges billions of years and connects us intimately to the very heart of our home planet. Subscribe to join us for more geological adventures and continue to explore the breathtaking saga of Earth's past, present, and future.